Look at the phone in your pocket, the laptop on your desk, the car humming quietly at a red light. All of them run on the exact same invention, a rechargeable battery small enough to carry, powerful enough to matter, built from a chemistry so delicate that billions of atoms slide in and out of it every single day without you ever noticing. This is the story of how that battery came to exist, and it took 3 men, 3 countries, and 15 stubborn years. Before 1991, nothing like it existed. Portable electronics ran on heavy, weak, disposable batteries or rechargeable cells so bulky and short-lived that portable was a stretch of the word. A powerful battery you could recharge hundreds of times, small enough to fit in your hand, seemed like a problem chemistry hadn't solved, and might not solve for a very long time. The story that finally solved it doesn't start with one flash of genius. It starts with an oil crisis, runs through 3 separate laboratories on 3 continents, and ends decades later on a stage in Stockholm. Along the way, it very nearly failed at every step, abandoned once for catching fire, patented but given away for free, and nearly buried again by a chemistry still not quite safe enough. It's worth knowing, before we start, where this ends. In 2019, 3 men would share the Nobel Prize in chemistry for this invention, and one of them would become, at 97 years old, the oldest person ever to win a Nobel Prize in any category. But in the 1970s, none of that was remotely in view. There was just a global panic about running out of oil. In October 1973, an oil embargo hit the United States. Gas stations ran dry. Prices for fuel and electricity spiked overnight. A country that had barely thought about where its energy came from was suddenly desperate for alternatives. Any alternative to imported oil. Even the oil companies themselves quietly began funding research that had nothing to do with oil at all. One of those companies was Exxon. Flush with cash and worried about its future, Exxon Research and Engineering built out laboratories to explore energy storage and alternative power, batteries, solar cells, anything that might matter if oil became scarce or ruinously expensive. Into one of those labs, in 1972, walked a young British chemist named M. Stanley Whittingham. Whittingham had earned his doctorate in solid-state chemistry at Oxford, then spent 4 years at Stanford studying something deceptively obscure, how ions move through solid materials, slipping between atoms without breaking the material apart. It sounds abstract. It would turn out to be exactly the missing idea batteries needed. At Exxon, Whittingham began studying a compound called titanium disulfide, TiS2, first explored for its odd electrical properties. But its real magic was structural. It forms as thin, stacked sheets, like an endless deck of cards with just enough space between each layer to slip something else inside. Whittingham realized something remarkable. Lithium, the lightest metal on the periodic table, eager to give up an electron, could slide into the gaps between those TiS2 layers and slide back out again without wrecking the host structure. Chemists call this intercalation. It's like slipping a coin between the pages of a book again and again without ever tearing a page. That reversibility is everything. Most batteries wear out because their chemical reactions change the electrodes permanently, a little more each cycle, until they simply stop working. Intercalation barely disturbs the host material at all. In principle, you could do it thousands of times. That principle is the seed of every rechargeable lithium battery that followed. Pair a TS2 electrode with a lithium metal electrode on the other side, add a liquid that lets ions travel between them, and you have a working cell. Lithium ions leave the metal, cross the liquid, and slot into the TS2 layers as the battery discharges, then get pulled back out again as you recharge it. In 1976, Whittingham published the result in the journal Science, Electrical Energy Storage and Intercalation Chemistry. It described the first practical rechargeable lithium battery ever built, a genuine breakthrough, quietly printed on a few pages of a journal almost nobody outside the field would ever read. Whittingham's cell ran at just over 2 volts, modest by later standards, but already ahead of the rechargeable batteries then in common use. And because lithium is so light and so reactive, the theoretical energy you could pack into a lithium battery dwarfed anything built from lead or nickel. On paper, this was a giant leap. Compare it to what existed. Lead-acid batteries, the same basic chemistry as a car battery, stored only around 35 watt-hours per kilogram. Nickel-cadmium cells, the rechargeable standard of the era, managed maybe 60. Lithium, the lightest and most energetic metal available, promised something far beyond either. But theory and a working product are 2 very different things. Every time Whittingham's cell recharged, the lithium metal electrode didn't plate back on smoothly. It grew unevenly, tiny metallic spikes called dendrites, creeping across the cell like frost on a window, thin and sharp and dangerous. If a dendrite grew far enough to touch the other electrode, it would short-circuit the cell internally, and with a metal as reactive as lithium, packed with stored energy, that short circuit could mean a sudden burst of heat, a rupture, even flame. The very property that made lithium so promising made it genuinely hazardous to handle at scale. It wasn't hypothetical. Cells in Exxon's own labs reportedly caught fire on more than one occasion, badly enough that the local fire department became unwelcome regulars at the building. Whatever Whittingham had discovered, it was not yet something you could safely hand to an ordinary consumer. Titanium disulfide had its own headaches too. It was expensive to produce, around $1,000 a kilogram in the money of the day, and had to be made and handled in completely dry, oxygen-free conditions. Exposed to ordinary damp air, it reacted to release hydrogen sulfide, toxic and famous for smelling like rotten eggs. By the early 1980s, the oil crisis that had justified all this expensive research was fading. Prices fell, panic subsided, and corporate patience ran out. Exxon judged the rechargeable battery business too small and the lithium metal safety problem too large to solve quickly. Quietly, the whole program was shut down. Whittingham had proven the core idea, that lithium ions could shuttle reversibly in and out of a solid host, was real and it worked. What remained was simple to state and brutally hard to fix. Find a cathode with a better voltage and an anode that would never grow a dendrite at all. An answer to half of that problem was already forming, 4,000 miles away, in England. The chemist who would solve half of that problem was already, by the late 1970s, a scientific legend for entirely different work. John Goodenough had trained as a physicist, helped develop key theories of magnetism and solid materials at MIT's Lincoln Laboratory, and in 1976 crossed the Atlantic to lead Oxford University's Inorganic Chemistry Laboratory. Goodenough heard about Whittingham's TiS2 battery, its elegant intercalation trick, and its dangerous, fire-prone lithium metal anode. As a physicist who understood exactly how electrons behave inside different chemical bonds, he had a hunch about where the real problem lay, not with lithium at all, but with the cathode material Whittingham had chosen. Sulfur, he reasoned, doesn't hold on to its electrons very tightly, which caps how much voltage a sulfide cathode like TiS2 can ever deliver. Oxygen is far greedier for electrons. Build a compound with the same lithium-friendly layered structure, but from a metal oxide instead of a metal sulfide, and the chemistry itself should allow a dramatically higher voltage. It was a bold substitution to propose. Nobody had shown that a lithium oxide compound could reversibly give up and take back lithium ions the way TiS2 did. Goodenough set out, with his Oxford team, to find one, testing candidate after candidate among the transition metal oxides. Joining him was a visiting researcher from Tokyo University, Koichi Mizushima, along with colleagues Philip Jones and John Wiseman. Through 1979 and into 1980, the team synthesized and tested one layered oxide after another, measuring how much voltage each could hold against lithium. They landed on lithium cobalt oxide, LiCo-O2. Like TiS2, it had a layered structure lithium ions could slip into and out of. Unlike TiS2, it held those ions at a voltage nobody had achieved before in a rechargeable lithium cell, exactly the compound Goodenough's reasoning had predicted should exist. Whittingham's TiS2 cell had run at a little over 2 volts. Goodenough's LiCo-O2 cell ran at close to 4, nearly double. In a battery, energy stored is roughly voltage multiplied by charge capacity, doubling the voltage, for a similar amount of charge, meant nearly doubling the usable energy packed into the very same cell. Think of what that meant in practice. The same size and weight of battery could now, in theory, run a device for nearly twice as long, or run a more powerful device for the same length of time. Voltage sounds like a dry technical number. In a battery, it is very close to the whole point. At the heart of both Whittingham's and Goodenough's designs sat the same idea, now sharpened, lithium ions leaving a layered host on charge, sliding back into it on discharge. Energy stored and released, not by breaking the material apart, but by ions gently rocking in and out of it, like a chair rocking on its own frame. But notice what Goodenough's 1980 design still required: a metallic lithium anode on the other side of the cell, the exact same ingredient responsible for Whittingham's dendrites and fires. A higher voltage cathode paired with the same unsolved hazard meant an even more energetic, and if anything more dangerous, battery than before. There's a quieter twist to this chapter. Oxford's own administration wasn't especially interested in patenting Goodenough's discovery. To get the patent filed at all, Goodenough had to sign away his own personal royalty rights, letting Britain's Atomic Energy Research Establishment take out the patent in 1981 instead. That patent would eventually be worth a genuine fortune once lithium-ion batteries conquered the world, money that flowed to the institutions holding the license, not the man who'd worked out the chemistry. It's a pattern that runs through this whole story. The inventors, again and again, were not the ones who got rich from the invention. And in the early 1980s, still nobody wanted to manufacture it. A cathode with a wonderful new voltage, paired with the same metallic lithium anode that had already scared off one oil giant, was not a product any company was eager to build and sell to ordinary customers. Goodenough kept working, eventually moving to the University of Texas at Austin, where decades later he would help discover still more cathode chemistries. But as of the early 1980s, the safe anode problem he and Whittingham had both run into remained completely unsolved. Meanwhile, on the other side of the world, an entirely separate line of research was underway in Japan. Not about batteries at first, but about a strange new class of materials just discovered by chemist Hideki Shirakawa. Plastics that could conduct electricity, called conductive polymers. Working with materials like these was a chemist named Akira Yoshino. Born in Osaka, trained at Osaka University, he had joined the Asahi Kasei chemical company in 1972, the very same year on the other side of the planet that Whittingham joined Exxon. Neither man had ever heard of the other. In 1981, Yoshino began exploring a battery built around one of these new conductive polymers, polyacetylene, as the anode. Paired with the right cathode, he believed, it might finally offer a safe alternative to metallic lithium. He didn't yet know that the right cathode had already been sitting in a published paper from Oxford for over a year. By 1983, Yoshino had built a working test cell, sealed inside a simple glass tube, Goodenough's lithium cobalt oxide as the cathode, polyacetylene as the anode. It worked. No metallic lithium anywhere in the cell. For the first time, someone had built a functioning battery entirely free of the dendrite problem. But polyacetylene had its own fatal flaws. It was too light and bulky for the amount of charge it could actually store, and it degraded chemically over time. A clever proof of concept was not the same thing as a battery you could put in a product and sell for years. Yoshino needed a completely different material for that anode, something dense, chemically stable, and still able to soak up and release lithium ions endlessly without ever letting a single atom of metallic lithium form. So he began a methodical, unglamorous search through every carbon material he could get his hands on. Yoshino and his team ultimately tested more than 100 different carbon-based materials, one after another, looking for exactly the right combination of properties, dense enough to be practical, stable enough to survive hundreds of cycles, and structured just right to host lithium ions without ever letting them plate out as bare metal. The ideal material needed to behave almost like a sponge for lithium ions, soaking them up at a nice low voltage when the battery charges, then releasing them smoothly back out when it discharges over and over for years without falling apart. Yoshino landed on a form of soft carbon made from petroleum coke, a cheap, abundant byproduct of oil refining with a loosely stacked molecular structure that left just enough room between its carbon layers for lithium ions to slip inside. Petroleum coke could take up lithium ions reversibly at a very low voltage, around half a volt relative to metallic lithium, behaving almost like a true rocking chair host, just like the cathode on the other side of the cell, only working in reverse. Here was the crucial insight. Pair lithium cobalt oxide, the ion source, with petroleum coke, the ions sink, and lithium ions would simply shuttle back and forth between two solid stable hosts every time the battery charged and discharged, never once needing to exist as loose metal in between. This is the full picture chemists now call the rocking chair battery, sometimes the shuttlecock battery. On charge, lithium ions leave the cobalt oxide layers and slot into the carbon layers. On discharge, they slide right back. The chair simply rocks between two fixed points. Nothing ever grows, nothing ever plates. Because there is no metallic lithium anywhere in the finished cell, there's nothing left to grow into a dendrite, the single flaw that had doomed Whittingham's design at Exxon, and that still lurked unsolved inside Goodenough's higher voltage cell. Yoshino's carbon anode didn't improve the danger, it eliminated it. There was a manufacturing bonus too, because both electrodes could be assembled already holding their resting share of lithium. Rather than starting with dangerously reactive bare metal, the whole cell could be built in a safer, simpler, more industrial-friendly way from the very first step on the factory floor. In 1985, Yoshino filed the patent describing this exact configuration: a lithium cobalt oxide cathode, a carbon anode, and a safe supporting electrolyte. On paper, this was, in essence, the modern lithium-ion battery, the design that, refined but intact, still sits inside nearly every rechargeable device on Earth today. Through 1986 and 1987, Asahi Kasei had small test batches built, and safety trials followed, the kind of dramatic demonstrations, like driving a nail through a cell or crushing it outright, that show a battery failing safely instead of catching fire. Yoshino's design passed tests that would have destroyed a lithium metal cell instantly. Because ions merely rocked between two stable hosts, rather than plating raw reactive metal, Yoshino's cell could be recharged not dozens but hundreds of times, with only a gradual, gentle decline in how much energy it could hold. This was the missing piece that finally made lithium batteries genuinely durable. Look at what it took, altogether, Whittingham's discovery that lithium ions could shuttle reversibly into a layered host at all, Goodenough's insight that an oxide cathode could hold nearly double the voltage, and Yoshino's patient discovery of a carbon anode that made the whole thing safe. Remove any one piece and there is no battery. Yet, even a brilliant, fully working patent is not the same thing as a product. turning delicate laboratory chemistry into something manufactured reliably by the million, packaged safely and sold at a price ordinary people could afford, is its own entirely separate kind of hard problem. Asahi Kasei was a chemical company, not a consumer electronics maker. It had no factory line for building finished batteries. So a chemist there, Kuribayashi, reached out to Sony, whose engineers had spent years separately chasing a workable, rechargeable lithium chemistry of their own without quite cracking it. Sony had assigned several internal teams to different candidate lithium chemistries. One of them, led by an engineer named Yoshio Nishi, zeroed in on essentially the same combination Yoshino had already patented: lithium cobalt oxide paired with a carbon anode. From around 1987 to 1989, Nishi's team ground through the unglamorous essential engineering: how to mass-produce cathode powder to a consistent quality, how to heat-treat the carbon just right, how to formulate a stable liquid electrolyte, and how to build safety vents into every single cell. It's the kind of work that almost never wins prizes. No elegant equation, no single eureka moment. But without it, the most beautiful chemistry in the world never reaches a single customer's pocket. Commercialization is its own, quieter form of genius, and this story would eventually forget to fully credit it. In February 1990, Sony announced the technology publicly and shipped sample cells to select customers for testing through the rest of that year. The quiet, unglamorous final steps before something entirely new reaches the world. In 1991, full mass production began at Sony's plant in Koriyama, in Japan's Fukushima prefecture. After 15 years, 3 laboratories, and at least 2 abandoned near misses, the modern lithium-ion battery was at last a real, mass-manufactured product. The very first product to use it was almost comically modest: Sony's own CCD TR1 video camcorder, a bulky, battery-hungry gadget that, almost overnight, became noticeably lighter and ran noticeably longer. Nobody filming a birthday party that year had any idea they were holding a future Nobel Prize. From that first camcorder, adoption spread fast. Sony sold over 100,000 lithium-ion cells before the end of 1991 alone, and more than 1 million the year after that. Cordless phones followed. Then, in the mid-1990s, laptops light enough to actually carry, and mobile phones small enough to fit in a pocket. Compare it to what it replaced. Nickel-cadmium batteries suffered from a notorious memory effect that shrank their usable capacity over time, contained toxic cadmium, and stored far less energy for their weight. Lithium-ion simply outclassed the old chemistry on almost every axis that mattered to a customer. Every year afterward brought small refinements: better cathode formulas, thinner separators, denser electrode coatings, each squeezing a little more energy into the very same size and weight of cell. None of it was as dramatic as the original 3 breakthroughs. All of it, added together, mattered enormously. Look at the whole arc on one chart. Lead acids roughly 35 watt-hours per kilogram, nickel-cadmium 60, nickel-metal hydrides 100, and lithium-ion, starting around 80 to 100 in those first Sony cells, climbing steadily toward 150 within just a few years of refinement. By the 2020s, the very best commercial lithium-ion cells reached somewhere around 250 to 300 watt-hours per kilogram, more than triple the energy density of those very first Sony cells, packed into a battery whose fundamental chemistry has barely changed at its core since 1991. But energy density alone doesn't explain why lithium-ion ended up everywhere. The other number that matters just as much, maybe more, is cost, and on that measure the story becomes almost unbelievable. In 1991, a kilowatt-hour of lithium-ion storage cost, by rough estimate, around $7,500. At that price, a battery pack big enough to power a family car would have cost more than the car itself, several times over. Lithium-ion, in 1991, was a technology for phones and camcorders. Genuinely wonderful, but nowhere close to affordable at any larger scale. Through the 1990s and 2000s, mass manufacturing scale, steady materials improvements, and increasingly fierce competition between Japanese, then Korean, then Chinese battery makers drove that price down year after year in a slow, unglamorous grind that got almost none of the attention the original invention had. By around 2010, tracked industry-wide, battery pack prices had fallen to roughly $1,100 per kilowatt-hour, still expensive, but for the first time low enough that a genuinely practical electric car started to look like real economics rather than a science project. By the 2020s, average lithium-ion battery pack prices had collapsed further still, down to somewhere around $130 to $130 per kilowatt-hour, a fall of roughly 97 to 98% from that first 1991 estimate in barely 3 decades. That single collapsing number is why an electric car battery pack, once a budget-shattering expense reserved for wealthy early adopters, becomes something an ordinary car buyer can genuinely afford within a single working lifetime. It's also why a battery large enough to store an entire house's worth of solar power overnight moves from science fiction to something a homeowner can actually buy and install, turning rooftop solar panels from a daytime-only novelty into round-the-clock power. Grid-scale battery installations begin appearing next to wind and solar farms too, storing surplus power for the moments the sun isn't shining or the wind isn't blowing, a role nobody designing a camcorder battery in 1991 ever imagined it would someday play. Consider that every one of these things, your phone, your laptop, an electric car, a cordless drill, a house battery, a chunk of the electrical grid itself, runs on essentially the exact chemistry Akira Yoshino patented back in 1985, refined but fundamentally unchanged. Meanwhile, the men who invented it simply carried on with their separate careers, mostly unaware just how vast the eventual impact would become. None of them set out, in the 1970s and 80s, to reshape the entire global economy of energy. They were just trying to solve a hard chemistry problem. Whittingham left Exxon for academia, eventually landing at Binghamton University in New York, where he continued researching battery materials for the rest of his career. Goodenough moved to the University of Texas at Austin, and remarkably was still coming into his office most days well into his 90s. Yoshino stayed at Asahi Kasei for his entire career, later admitting he never expected, back in 1985, quite how enormous this invention would eventually become, from a modest camcorder battery to the power source of the global energy transition. One name would end up conspicuously less famous than the other three: Sony's Yoshio Nishi, the engineer who led the unglamorous, essential work of turning laboratory chemistry into a mass-produced, reliable, sellable product. Nishi would later, publicly and pointedly, express his disappointment at being left off the prize this invention eventually earned. A footnote worth remembering: commercialization is its own form of brilliance, even when history's spotlight doesn't always fall evenly. Because, in October of a particular autumn, a phone rang in Sweden, and this quiet, decades-long relay race between three men who barely knew each other was about to receive its most famous and most surprising chapter yet. October 9, 2019, the Royal Swedish Academy of Sciences announces the Nobel Prize in Chemistry. The prize is awarded jointly to three men: M. Stanley Whittingham, John B. Goodenough, and Akira Yoshino, for the development of lithium-ion batteries. By then, Whittingham was 77, a professor at Binghamton University. Yoshino was 71, an honorary fellow back at Asahi Kasei. Both had spent decades since their original breakthroughs continuing to work on batteries, largely outside the public eye. And John Goodenough, 97 years old, became, on the very day of the announcement, the oldest person ever to receive a Nobel Prize in any category, in the history of the prize. Nearly 40 years had passed since his 1980 discovery at Oxford. 4 decades in which the chemistry he'd helped invent had quietly, invisibly conquered the world's pockets, bags, garages, and rooftops long before the world got around to properly thanking him. As it happened, Goodenough learned the news while in London, not at his usual desk in Texas, but there to receive the Royal Society's Copley Medal that same week. Told he'd also won the Nobel Prize, he simply said it had been a wonderful surprise. The Nobel Committee's official citation captures the arc of the whole story in a single sentence. These lightweight, powerful, rechargeable batteries, it said, had laid the foundation of a wireless, fossil fuel-free society. The very outcome that 1970's oil crisis had first set this whole search in motion to find. Pause on how strange and beautiful the whole chain of events really is. A chemist trained to study how ions move through solids. A physicist who understood electron energies well enough to bet on an oxide nobody had tried. An industrial chemist patient enough to test over 100 different carbons by hand. 3 different minds, 3 different countries, roughly 15 years apart, none of whom set out to share a prize together, or even necessarily to meet. Each one solved a problem the last had left unsolved, and only because all 3 pieces eventually lined up did any of it ever leave the laboratory. Trace the 2 numbers that tell the whole physical story. First, voltage. Whittingham's titanium disulfide ran at roughly 2.2 volts. Goodenough's lithium-cobalt oxide nearly doubled it, to about 4 volts, and every lithium-ion cell in your pocket today still runs on that same doubled voltage. Second, energy density, from lead-acid's modest 35 watt-hours per kilogram, through nickel-cadmium and nickel-metal hydride, to today's lithium-ion cells holding roughly 250 to 300, an almost tenfold leap achieved in well under half a century. And third, cost. From around $7,500 per kilowatt-hour in 1991 down through roughly $1,100 by 2010 to somewhere near $130 to $150 today, a drop of nearly 98%, the single number that explains why electric cars and grid batteries are suddenly, finally, everywhere. Tonight, when you plug in your phone, picture what's actually happening inside it. Billions of lithium ions leaving a layer of cobalt oxide, crossing a thin membrane and quietly sliding into a sheet of carbon, then rocking all the way back again tomorrow morning thousands of times across that one battery's life. That silent, invisible shuttle traces directly back to a shelled 1970s oil crisis experiment that once caught fire in an Exxon lab, an Oxford patent its own inventor was talked into giving away, and a Japanese engineer's stubborn, unglamorous 100-carbon search that nobody thought would matter. None of the 3 Nobel laureates got rich off royalties the way you might expect from a world-changing invention. The real fortune mostly flowed to the companies and institutions that manufactured and licensed the technology at scale. A quiet, recurring irony sitting right at the center of this story. But all 3 men lived long enough to see their invention genuinely reshape the modern world. A rare outcome most inventors never get to witness for themselves, and one worth sitting with for a moment before we close this out. The lesson tucked inside all of it: truly transformative technology almost never arrives complete from one single mind. It gets assembled, piece by piece, often by people who never meet, each one quietly solving the leftover problem the last person couldn't crack. Whatever comes after, lithium, solid-state batteries, sodium-ion, something nobody's discovered yet, will very likely follow the exact same pattern: an idea shelved too soon, a leap that improves it, and a patient engineer who finally makes it safe and cheap enough to matter to the rest of us. So the next time your phone lasts all day on one charge, or you glide silently past a gas station in an electric car, remember the quiet 3-decade relay behind it. If this story stuck with you, do 2 quick things. Hit subscribe. Neat Science brings another forgotten story back to life, and there's a whole playlist of them waiting for you right now. And tell me in the comments which part of this surprised you the most. I read every single one. So keep exploring. Your next story is just 1 click away. I'll see you there.